This conference will now be recorded.
Okay, hello. Can you guys hear me?
Yes, we can.
Okay. So thank you all for dialing in. My name is Hersh Nanda, and I'll be presenting about a science project that I worked on in school. I did some research on it, and I submitted it to an Informs National Conference, and it was also previously presented at the ASQ Phoenix section meeting in April. And I also wrote an article about my research, which has been accepted for publication in the ASQ Quality Progress magazine. And so I'll be presenting about my science project, where I used statistics to determine which factors are the most significant in affecting the rate of heart disease. So let's get into it. So before I get into my experiment, I'm going to give you an insight onto how prevalent heart disease is in the U.S. If you didn't know, it's the #1 killer in the U.S. When it comes to diseases. And so as you can see, there's a big difference between the high end and the low end. West Virginia has in West Virginia, around 8% of the population has heart disease, and of the population that was diagnosed with heart disease, and in Utah, 3% of the population. So the goal of this project was to find out what causes this variation in heart disease, and so I wanted to find out which factors can help with the decreasing the rate of heart disease in the U.S. And so my research questions were, which risk factors are the most significant causes for heart disease? And I used statistical analyses to prove this. Is there a positive or negative impact of the risk factors on heart disease? And can I create a mathematical model that shows how the risk factors are related to the rate of heart disease? And can I graphically show the correlations between the possible risk factors in heart disease? So before I get into the tests, I'm first going to tell you on which variables I included. I included around 15 variables, and so the independent variables that could possibly affect the rates of heart disease are on the left. I used, for example, I used fast food intake because it has been said that fast food intake is usually unhealthy, and that's why people don't usually eat it don't consume it on a daily basis, because it's usually not prepared very well, and it could possibly increase the risk of heart disease. Another one I included is frequent mental distress, for example. So that's the percentage of adults who reported by their doctor that it was not good for 14 or more days in the past 30 days, because it has also been said that stress may also lead to heart disease. And if I go down here, the three most significant ones that I assumed would be the most significant in affecting the rate of heart disease were high cholesterol, high blood pressure, and diabetes. And so if you didn't know, heart disease is actually caused by an accumulation of cholesterol in the arteries, and that can clog the arteries and prevent the blood from flowing, which ultimately leads to a heart attack. And so high cholesterol would probably definitely be a significant factor in affecting the rate of heart disease. And I included high blood pressure because that is also correlated with high cholesterol, which can also lead to heart disease. And it has been said that diabetes and heart disease are correlated with each other, and people that have diabetes are usually at greater risk of getting diagnosed with heart disease. And so there are three dependent variables here: heart disease was the primary one. There was cardiovascular disease deaths and heart attack. And so the dependent variable that I've used in this experiment is heart disease, which is the percentage of adults who reported being told by a health professional that they have angina or coronary heart disease. So the three things I used in this experiment are, well, first of all, you definitely need data on the risk factors in heart disease in order to run the test. And I used Minitab 17 as a statistical software in order to run the statistical tests. And I used Excel to organize my data. So before I get into the experiment, I'm going to talk about what terms that you as viewers will need to, as listeners will need to know. So the two tests I ran were correlation tests and regression tests. And so a correlation test is a test that shows if there's a relationship between two or more variables. Now, a correlation test does not show a cause and effect relationship between two or more variables. So an example of a correlation between two variables would be as a student studies more, they will get higher scores on their tests. So this shows that studying correlates with the test scores, and it's saying that if you study more, you'll get higher score on your tests. But this doesn't mean that studying will lead to a higher score on your test. Now, a regression test shows that if there's a cause and effect relationship between the two variables. So if I use it with the same example like before, in this case, if I run a regression test with that, studying and test scores, and it shows that they are related, then the regression test will basically tell you that if you study more, you will get a higher score on your test because studying has an impact on test scores. Two other terms that you will definitely need to know when it comes to correlation is p-value and Pearson's correlation coefficient. P-value is one of the two values that the correlation coefficient that the correlation test reveals in its results. It determines the appropriateness of rejecting the null hypothesis in a hypothesis test. I will not get into that, but I will talk about like the simpler version of what a p-value is. It's basically the amount of risk that you are willing to take in a statistical test. So a p-value ranges from 0 to 1. It is usually set at 0.05 when running a statistical test. And so 0.05, this value means that you're taking 5% risk when you're running a statistical analysis. And so when you get your results, these two values will be displayed again. The p-value, it'll tell you after the test how much risk was taken, and you usually don't want your p-value at the end of the test to be greater than the p-value that you set before, because that means you're taking more risk than you were willing to take, and you don't want to trust the results. The second value that you will get is the Pearson's correlation coefficient, and this assesses whether two continuous variables are linearly correlated. The Pearson's correlation coefficient tells you the strength of the correlation and the direction of the correlation. It ranges from -1 to 1, and so if the value is negative, that means that there's a negative correlation. If it is positive, that means it's a positive correlation, and if it is at the high end of the range from -1 to 1, then that means it is a strong correlation, and if it is close to 0, then that means it is a weak correlation. And I'll get more into that later on. R-squared adjusted, standard error of regression, and VIF are three values that we will deal with when I talk about the regression test. So I will not get into that right now. So before I ran my tests, I did some research on vegetarians when it comes to heart disease and meat eaters. So I found that vegans and vegetarians are usually thinner and have low cholesterol, have lower BMI, which is body mass index, and are overall healthier than meat eaters. and they have a less chance of getting heart disease. Methodology. So my data was compiled from 3 sources: CDC, which is Centers for Disease Control and Prevention; EPA, which is the U.S. Environmental Protection Agency; and a genomics and biotech company known as 23andMe, which is based in California. And the data from that company was published by Stanford University, so the data that I had compiled was pretty reliable. Using Minitype 17, I created 2D and 3D plots and models to visualize my data, and then I ran correlation tests and regression tests. So this is a matrix plot of the data, and so as you can see, there are many different plots. The factors are on the sides right here, and then heart disease is at the top. So a matrix plot is basically many scatter plots combined together into one big graph. So these different boxes are individual scatter plots. And so let's look at one scatter plot. So if we want to look at heart disease and diabetes, you can see that this is one scatter plot, and you can see that the data points are forming an upward sloping line. So this shows that there's a correlation between heart disease and diabetes, and it looks to be a positive correlation, because if you look at the different axes, as the diabetes value increases, then the percentages of heart disease will also increase. If we look at another one here, like obesity and exercise count, you can see that there's a negative correlation because the data points are forming a downward sloping line. So as people exercise less, they usually get more obese. And so these are individual scatter plots. So when it comes to scatter plots, there will be data points arranged in a certain form, usually in a sloping line. So as you can see in this picture, the data points are kind of arranged in a upward sloping line here. So you can see that as the smoking rates increase in value, there's a higher chance of getting heart disease. And here's an example of another negative correlation between 2 variables. So as you exercise more, your blood pressure decreases. So I'm going to talk about a correlation algorithm first, and then I will get into the regression test. So before you run a correlation test, you always want to visualize the data by creating scatter plots so you can appreciate the correlation between the 2 variables. It is much easier to visually tell if there's a positive or negative correlation between 2 variables, and then you can get into the specifics. So after you make a scatter plot, you want to and you run the test, you will get 2 values, like I explained before, the p-value and the Pearson's correlation coefficient. So the p-value is the amount of risk you're willing to take, and if the p-value at the end of the test is greater than the one that you set, which is usually 0.05, then that means that the Pearson's correlation coefficient must be ignored, and it is assumed that there's no correlation between the 2 variables. If your p-value turns out to be less than the one that you have set, in this case it was 0.05, then you can take into account the Pearson's correlation coefficient, and this tells you how strong the correlation is and what direction it is in. So let's look at one. So if you get a Pearson's correlation coefficient from between 0 to 0.4, it's a weak positive correlation. It is positive because, as you can see, there's no negative sign. So a negative correlation would be like here, it would have a negative sign. Here, there's no negative sign. You get a positive correlation, and it is weak because it is pretty close to 0. It is not close to 1. It is not really in between 0.4, 0.6. So that wouldn't be moderate. So this is a weak positive correlation. Now let's look at the opposite end of the spectrum. Let's look at a strong negative correlation. Strong negative correlations are usually from -1 to -0.6 because it is not close to 0, so it's not weak, and it is a negative correlation because you can see that these 2 values have negative signs. So I ran some correlation tests, and then after the correlation test, I ran linear regression tests to check if there's a cause and effect relationship between the variables. So when you run a linear regression test, you always want to visualize the data before you run the test. So you have, in this case, you should generate a matrix plot, which is many different scatter plots together. So you can check the relationship among the variables and between the variables and the outcome. After you generate a matrix plot, you want to check the model and assumptions. And so when you run a regression test, you will also get p-values and you will get variance inflation factors. So you first want to check the variance inflation factors and then get into the p-values. So variance inflation factor is basically the measure of how much multicollinearity there is between the variables. And multicollinearity is it's not good. You do not want it in your regression test. Multicollinearity is basically a correlation among the variables, which can skew data because if you have multicollinearity, then you don't know what is the root cause for the outcome. So you always want your variance inflation factor to be less than 5, and if it's less than, and if the variance inflation factor of certain variables is greater than 5, then you want to exclude those correlating factors because you don't want it to skew the results. Once you get rid of all the correlating factors, and all of your VIFs are below 5, you want to move on to the p-values, and you want to check that all of the p-values are less than 0.05 so that you are not taking more risk than you were supposed to. After you run a regression test, you want to check for residuals, which are basically errors. You don't want your residuals to have a pattern because that means that there's something wrong in your experiment. You want your residuals to be consistent, and you want your residuals to be random. So you know that there is no specific error in your experiment that is causing certain outcomes that are not supposed to be results. After you check for residuals, you want to check the quality of the model that you get in your results. You will get an R-squared adjusted value and an S value, which is standard error of regression. R-squared adjusted value basically tells you how reliable your model is. And so a good R-squared adjusted value would be around 70% to 100%. And anything below that means that your model isn't very reliable. And you will also get a second value called standard error of regression, is basically how much error is in your model. You want a very small amount of error in your model. And so the first test I ran was correlation. So here are some examples of the correlation results I got. So on the right, you can see that there's red boxes, yellow boxes, and blue boxes. So red boxes means that there's a strong negative correlation. Yellow boxes means that there's a moderate/weak correlation, and it can be positive or negative. And blue boxes means that there's a strong positive correlation. So let's look at an example for a red box. So let's look at weekly exercise and heart disease, number 4. So as you can see here, by the way, in the correlation test, when you get the results, the p-value is always going to be at the bottom, and the Pearson's correlation coefficient is going to be at the top. So if we look at number 4, you can see the correlations between the weekly exercise count and heart disease rates. So you can see that the p-value is below 0.05, which is good. That means we're not taking much risk. And so once you check that the p-value is less than 0.05, you move on to the Pearson's correlation coefficient, and you can see that they are negatively correlated, which means that as weekly exercise count decreases, then the rate of heart disease increases simultaneously, or vice versa. So you can see that this is a strong positive correlation because it is between 0.6 and it's between negative 0.6 and negative 1, and this is actually a strong negative correlation because you can see that there's a negative sign. And so let's look at a strong positive correlation. Diabetes and physical inactivity, box 16. So you can see the p-value is less than 0.05, which means we're not taking much risk at all. And we move on to the p-value, and you can see that it's 0.8, which is a very strong positive correlation. Or sorry, this is not the p-value, this is the Pearson's correlation coefficient. So this shows that this is a strong positive correlation. It is between 0.6 and 1, and it does not have a negative sign. So this is a strong positive correlation. The ones that don't have boxes around them are the ones that have a p-value that is greater than 0.05, or they're ones that that haven't been like discovered to be correlated yet. So an example of one that where there is no correlation between the two variables would be pollution and heart disease, so you can see here the p-value is greater than 0.05, so you have to ignore the Pearson's correlation coefficient, and so that means that there is no correlation. Here's also some more results from my correlation tests. You can see these are strong positive correlations. High cholesterol and heart disease have a strong positive correlation, along with blood pressure and heart disease. And so does mental distress and heart disease too. So after I ran my correlation test, I ran a regression test. And so as you can see here, there are the four values that are displayed here that I talked about before. You get an R-squared adjusted, an S value, a P value, and a VIF. So when you're running a regression test that includes multiple variables and not just two variables, you don't want to look at these, because these two values are only for regression tests that only include two variables. And so when it comes to a multiple linear regression test, you want to look at the R-squared adjusted. And so you can see here that the R-squared adjusted is 82.16%, which is good. You want your R-squared adjusted to be high so that you know that your model is reliable. So in this case, it was 82.16%, which is good, which means that the model is reliable. And S stands for standard error of regression, and here you can see it's 0.44, which is very low, which is what you want when it comes to regression tests. And so you also get a variance inflation factor and then p-values. And so before, when I first ran regression tests, all of the variables were listed here, but many of the variables had VIFs greater than 5. So I had to exclude those variables, run the test again, and get rid of all the variables with VIFs of 5. And then once I got rid of all of those, you have to look at the variables that had p-values that were greater than 0.05. And then I excluded all of those variables. And then you're left with these four variables: smoking rates, vegetable consumption, high cholesterol, and frequent mental stress. So as you can see here, all of the VIFs are below 5, and the p-values are all below 0.05. This one doesn't matter here because this is just a constant, so this is not one of the variables. And so after the test, you can see that these four variables are remaining, which means these four variables are likely to be responsible for the rates of heart disease. So smoking rates, as you can see, it has p-value and VIF that's normal. And so you can see that smoking rates, vegetable consumption, high cholesterol, and frequent mental stress are significant factors that affect the rate of heart disease. And so after you run your model, you always want to do a residuals analysis to check for errors. So as you can see here, in these two graphs, you will get 4 graphs. So in these two graphs, you want to check if there are patterns throughout the graph. And so as you can see, there's random error, which means that there is not much error. And here, there's also random error. There's no upward sloping line or downward sloping line or any form of a pattern, which means that the error is consistent, which means that there is nothing wrong with my model. And then you will get 2 other graphs called normal probability plot and a histogram. So you want to check if the data is normally distributed throughout the graph. So for example, in this case, you can see the data is pretty close to the line, which means that the data is reliable and there's not much error. Now, if the data was spread out and wasn't really it wasn't really following the line, then that means that something's wrong with the graph. And then in this histogram, you want to check if there's a bell curve, usually in the middle. If it's somewhere on the side like this, then that means the data isn't very normally distributed. And if the bell curve isn't really forming, then that means the data is also not normally distributed. So this tells me that my data is reliable and my model is also reliable, and there's not much error. And so after running the regressions test and the residuals analysis, I built an equation. So you can see heart disease is equal to negative 1.58. This is just the constant, plus 0.0861 smoking rates minus 0.1423 vegetable consumption, plus 0.1360 high cholesterol, plus 0.1891 frequent mental stress. So this tells me that if there's a 1 unit increase in smoking rates, then that means the heart disease rates will increase by 0.0861. And so if you look at all 4 of these factors, you can see that this one has a positive sign, this one has a positive sign, and this one has a positive sign. That means these 3 factors are positively correlated, and they also positively affect the rates of heart disease. And vegetable consumption has a negative sign, which means that if, for example, if there's an increase in vegetable consumption, then the heart disease rates will decrease, which is good. So that means these three factors are not good. Vegetable consumption is good, and it helps decrease the rates of heart disease. And so if I look at my results, you can see the most significant factors are smoking, lack of vegetable intake, frequent mental distress, and high cholesterol. So lack of vegetable intake, if you don't eat many vegetables, it could definitely threaten diagnosis with heart disease. And so then if we look at my correlations, you can see there's correlations, strong positive correlations between heart disease, diabetes, smoking, physical inactivity, etc. And so these are all my correlations. Strong negative correlations between heart disease, medium household income, exercise, food, and vegetable consumption. So if you are planning on trying to improve your health and decreasing your chance of diagnosis, then you would want to do these things. Some of these may not work because it's a correlation, but vegetable consumption will definitely work because I ran a regression test and it said that there's a cause and effect relationship. And then there's also 81 other correlations and interesting findings between the factors, but I will not list them all here. So conclusions, I talked about this. For every 1 unit increase in vegetable intake, rate of heart disease will decrease by 1.423 units. For every 1 increase in cholesterol, heart disease will increase by 0.136 units. Different values here, different values here. And so R-squared adjusted and standard error told me that my graph was reliable and my regression test worked. And so after I ran my regression test, I made a surface plot just to show the correlation between 3 variables. So here you can see as smoking rates and high cholesterol increase, heart disease rates also increase. So this is also a cool tool that you can use to view the correlation among 3 predictors. And I also am currently writing an article about surface plots, which I will be submitting to ASQ to a magazine. And so these are my references. This is where I got my background research, and then here are my data sources. And thank you for letting me present here. Are there any questions?
Thank you very much, Hersh. First off, congratulations on having your article accepted by ASQ. That's quite well done.
Thank you.
Folks, if you have any questions for Hersh based on what he just spoke about, feel free to use the chat box. I know we're running a little bit over here. It's about 11:15 in the East. but that's good and bad that it's on Saturday.
So if there are any questions, you can type in the chat box. Thank you, Linda. So are there no questions?
There is a question here. How long did it take you to collect all of the data?
It took me quite some time, actually. It took me like around 1 or 2 months to collect all the data. I had to look at many different sites. I had to go to many different sources and look at many different articles. So it did take quite some time to compile all of the data.
Okay.
All right. Thank you. Are there any more questions? Okay.
At the moment, there does not appear to be any. If there are later, if somebody does have a question later, I guess it's. I would think it's. Go ahead.
I can provide my email if anyone wants to ask any questions later on.
Yeah, that'd be fine. Or if they do have questions too. Oh, wait a minute. Let's see what else we got here. Just a couple of comments saying that that you were excellent. So.
Yeah. Yeah. Thank you, everyone.
Anyway, yep, and thank you. If there are no other questions, we're going to go ahead and get things wrapped up. I'd like to thank both Vic Nanda and Hersh Nanda for presenting for us on this Saturday. I know it's kind of hard sometimes to get folks who may be busy on the weekend to want to spend time online, but we appreciate everyone turning out today, and as well as Vic and Hersh. So without any further delay here, I guess we're going to go ahead and wrap things up. Thanks everyone for joining us, and keep in mind our next webinar will be on Wednesday, November the 14th. It'll be the 100th webinar for Blue Ridge, and we hope many of you can join us then. There are still plenty of seats available, so please do register if you are interested in joining us on Wednesday. It'll be 12 noon Eastern time, normal schedule too, so be in midday. So looking forward to many of you joining us, and until then, hope everybody has a great rest of the weekend, and we'll see you hopefully online soon. Thanks. Bye now.
Thank you.
Thank you. How are we?